Bismillahirrahmanirrahim. Today's topic is bandwidth of angle modulated waves from the chapter Angle Modulations, and the course title is IEEE 351-352 Analog/Principles of Communication Systems. I am Dr. Zishan Karim from ECE Department CUI WA campus. Okay, let's start with the lecture contents. In this video we will focus on types of frequency modulation with respect to bandwidth. There are two main types. One is called the Narrowband FM and the other is called the Wideband FM. So these two types are very important because it their usage will directly affect the use of a bandwidth in a system. And finally we will derive the bandwidths using the Carson rule. So these are lecture contents which we discussed briefly. So let's move to the detailed lecture. Okay, as I mentioned, there are types of angle modulation or the frequency modulation with respect to bandwidth. First is the narrowband frequency modulation. So, as we are familiar with this equation phi FM, this is the frequency modulated signal equation, which is A cos, and this was phi which we derived. So phi omega c or 2 pi f c t, because we previously did calculation in 2 pi. So 2 pi f c t plus kf, right, and the integration of a message signal, right, 0 to t and m of alpha or any variable which you like to assign here, right. So this is similar to that. So this is our FM equation. So for signal to be a narrow band, there is a condition that the amplitude of this part kf into mf, kf into the message signal should be less than 1. So this is the important condition. If this is very less than 1, then we can name it as a narrowband FM, or we will have a narrowband FM signal. As its name suggests, narrowband actually means that it will consume less bandwidth. It will consume less amount of bandwidth, less bandwidth, BW, right? So, if we consider that the let k of f m of f d alpha is equal to k of f sin omega mt, if we have a cos signal here, for example, the single tone signal, then if we integrate, then we can get approximately kf sin omega mt. So in this case, the bandwidth of a FM signal will be approximately equal to 2fm or 2b, because this is a massive signal. So massive signal bandwidth, we can see that from the spectrum, like this is our carrier frequency and this is fc plus fm and fc minus fm. So total bandwidth here will be, we have a 2b, right? So 2fm or 2b. So this will be the bandwidth. The other condition, this is fm. Narrowband FM requires that beta should be less than 1 radian, typically less than 0.2 radian, or but should be less than 1, very less than. So usually they take 0.2 or lesser value than 0.2 radian. So you know that the beta can be calculated as delta f over fm is equal to delta f over b. So this is the modulation index equation which we already derived in the previous lectures. If you are not familiar, then please go to the previous videos. Okay, so this this spectrum is plotted for b equals to 0.2, so it is less than 1. So you can clearly notice that there are two side bands. One is the upper side band, the other is the lower side band. So it is similar to the uh, amplitude modulated signal, which we already studied. So for a narrow band frequency modulated signal, the bandwidth is around 2B, which is similar to the AM signal, which we already studied, right? So narrowband FM is the FM wave with a small bandwidth. As I told you, the modulation index of a narrowband FM is small as compared to 1 radian. We already discussed. Hence, the spectrum of a narrowband FM consists of the carrier and the upper sideband and lower sideband. For example, carrier in the center, upper sideband, lower sideband, right? And the modulated bandwidth of a narrow bandwidth FM is 2 Hz, same as the AM. The sidebands of FM has a phase shift of pi by 2 as compared with AM, which has no phase shift. We will prove this in the next slide, that how the what is the difference between FM and the AM. So this mentioned that they have a FM has a phase shift of pi by 2 as compared with AM, which has no phase shift. So when we have a FM signal, there is a phase shift of pi by 2, whereas there is no phase shift of pi by 2 in AM signal, but they have a same bandwidth. Okay, let's move to the other slide. Okay, let's start with the narrowband FM equation derivation. So start with the equation for the tone FM. So for tone FM, tone means that we have only a single frequency component, no harmonics are involved, only fundamental frequency. So FM is the fundamental. So we already proved that phi narrowband FM equals to AC cos 2 pi FCT plus beta sine 2 pi FMT. If you are not familiar, then see my previous video where we derived this equation, right? So extending this equation using trigonometric identity, which is cos alpha plus beta, you know that cos alpha plus beta is equal to cos alpha cos beta minus sin alpha sin beta. Using this one, so this one will be alpha, this one will be our beta. Second angle A, first angle, second angle. So cos alpha cos beta minus sin alpha sin beta, right? So you know that in narrowband FM, the condition is that beta should be very less than 1. So we suppose that here beta is approximately equals to 0. Because it is less than 1, it can be 0. So we select beta equals to 0 here, and for example cos beta sine 2 pi FMT is very less, so it's approximately equal to 1. We called it approximately equal to 1. So when we put it 0, so cos 0 is equal to 1. And sine beta sine 2 pi FMT, if this is 0, then sine of 0 is 0. So right, so if inside term is equal to 0, so we can in other words say that beta sine 2 equals to beta sine 2 pi FMT, because both are 0, so left hand side are equal to right hand side, so we can say that beta sine 2 pi f is equal sine of this is equal to approximately equal to beta sine 2 pi FMT. So phi narrow band FMT we can write after using this in equation 1. For example, we name it as equation 1. So putting 1 for here and beta sine 2 pi FMT only here. So we will get A C cos 2 pi FCT minus beta sine 2 pi FCT into sine 2 pi FMT. Now here there is another trigonometric identity, sine alpha sine beta, which is equal to half cos alpha plus beta minus cos alpha minus beta, right? So just by adjusting the signs, AC cos 2 pi FCT as half beta AC common, taking AC common here. Now there was AC here as well, so this was missing. So half beta AC cos 2 pi, right, FC plus FM minus cos 2 pi FC minus FM. So this is equation of narrowband FM for a single tone modulation. Similarly, we already have an equation for amplitude modulation with a tone frequency, which is AC cos 2 pi FCT plus half mu. This was mu modulation index AC cos 2 pi FC plus FM cos 2 pi plus cos 2 pi FC minus FM. This was for AM. Now you can clearly notice that these two equations are similar, almost similar, because there is a modulation index, there is also a modulation index. the rest equation looks similar except this sign minus and positive. So this sign represents the phase difference. So the difference in the sign, that is the phase of difference, we consider. So we clearly notice from this that we have a different phase here, but the bandwidth is similar. So the narrowband FM bandwidth is comparable to that of AM, which is equal to 2 FM. But we have an opposite phase shift. So this point should be remembered. Oh, this is the comparison of a spectrum. This is AM signal, amplitude modulated signal in time domain, and this is their spectrum. This is carrier, and this is upper sideband, lower sideband, right? And this is the negative reflection of this spectrum, right? So similarly, for narrowband FM, we plotted a spectrum, and you can see that the modulated signal here is different in time domain, but in frequency domain, if you notice that they are similar, exactly similar. So with different phase, because here no phase is plotted, so this is only the amplitude. So in amplitude uh, they are similar, maybe with some value little bit less or more, but at same point they have a FC plus FM and FC minus FM, so only 2B bandwidth, but their phase will be different. Okay, let's move to the wideband FM. As the name suggests, it will take more bandwidth as compared to the narrowband FM. So let's start with the single tone message signal for the wideband FM as well. So message is single tone AM cast 2 by FMT. So for a wideband FM, we can write SFMT equals to a real AC in terms of exponential is exponential j 2 pi FCT plus j sine j beta sine 2 pi f. This equation is similar to the uh, narrowband FM, but in terms it is written in terms of exponential. So when we need to expand the exponentials into a Fourier series, so that we can analyze FMT. So to analyze these equations, we need to find the Fourier. So for Fourier, because this is usually a non-periodic wave, we can't directly find the Fourier easily. So there are a number of steps which we ignore the detail here, the detailed steps. So for a wideband FM in time and frequency domain for a single tone, we can write this in terms of a Bessel function. So here the Bessel's function are involved. So in time domain, this equation can be, after analyzing using the Fourier series, can be written as this one. This is the wideband FM modulated signal equation, right? Previously we derived the narrowband FM. So here we just ignore the detailed steps because these steps are too much complex, and here we don't require this kind of derivation. So St equals to, in terms of Bessel function, if we write, so St equals to AC summation n equals to minus infinity to plus infinity, and these are the Bessel's amplitude coefficients, j and beta. So n ranges from minus infinity to infinity, and beta, you know, is the modulation index. So from here we can notice that for different betas we have a different Bessel's values or Bessel functions for varying n. So uh, here the varying n is, these coefficients are similar to the previous coefficient which we used in the narrowband FM. What was that? That was the amplitude of that narrowband FM wave. For example, if you plot this one, this is your carrier and this is your sideband, right? So how you know this amplitude? How much height this sideband will have? So previously we have amplitude for that one. So in case of wideband FM, we will use J and beta to calculate these amplitudes. These are sidebands amplitude actually, right? So this is a time domain. In frequency domain, AC by 2 summation n equals to this J and beta. And frequency domain, when we expand it, it becomes uh, delta function, impulse function. So f minus fc minus n fm, f plus fc plus n fm, right? So where coefficient j and are Bessel function. Okay, in theory, for wideband FM, there are infinite number of sidebands. If anyone asks that what is the bandwidth, theoretical bandwidth of wideband FM, the answer is it's infinite because it has infinite number of sidebands and hence required infinite number of amount of bandwidth, right? Whereas in practice, wideband FM is limited to finite number of sidebands with significant power. Usually because you know that there is a significant power or there is a noise threshold which we call for example, this. Below this we will consider the system noise, right? So above this is a significant bands. For example, here we consider three significant bands, right? Side bands, and there are other bands as well, but these bands power is below the noise, so we call we consider them as a noise. So in practice, wideband FM is limited to the finite number of sidebands. So here we have a three with significant power. We called it significant because whereas the other bands are treated as noise because they are below the noise figure, right? Below the noise limited power. So we can't differentiate between the noise and the sidebands. So spectrum of empty when empty is a single tone for a single value of beta. For example, we have a fixed beta and varying n. So J, for example, here we have a 3n and 0, 1, 2, right? 3. So FC, FC plus FM, and FC plus 2FM. There are three significant bands, and the amplitude of these bands depends on these values. Coefficient J2 beta, J0 beta, J1 beta. So you can notice that these values are different, right? J1 is different, J2 is different. Similarly, their negative part J minus 1, J minus 2. And this is the overall negative image of this complete spectrum. So minus FC and minus FC plus FM minus FC minus FM, right? So this is the spectrum of a single tone wideband FM. So what we conclude from here that in real the wideband FM has an infinite number of sidebands, but in practice we just limit to the finite number of sideband with a significant power. Now the question arises, what will be their bandwidth? So let's discuss how to calculate the bandwidth of a wideband FM. Okay, uh, so to conclude with, FM has a side frequencies extending to infinity frequency, theoretically infinite bandwidth, but side frequency become negligibly small beyond a point called the practically finite bandwidth. And FM signal bandwidth equals to the required transmission bandwidth, right? So bandwidth of FM signal is approximately defined by using Carson rules, which gives the lower bound, right? So what is the Carson rule? So Carson rules say that nearly all power lies within the low bandwidth, which we mentioned that there can be infinite number of side bands, but there is a significant side bands which usually lies in the lower portion of the bandwidth, and either even though it extends to the infinity, but these these are not above the noise floor, so they are considered as a noise. So for a single tone message signal with frequency FM, the bandwidth is calculated using Carson rules. So this was proved by Carson. So we just have to remember that total bandwidth is equal to 2 delta F. So delta F is a frequency deviation plus 2 FM. So this is a message signal of frequency. So if we write in terms of beta, so equals to by taking common FM, so equals to 2 beta plus 1 into FM. You can easily prove that how it becomes 2 delta F from 2 delta F plus 2 FM equals to 2 beta plus FM. So if you just take common FM, so then delta F over FM, you know that delta F over FM is equals to beta, right? So if you take common FM here, so it means that you need to divide by FM here. So delta F over FM becomes beta. So here you divide, you take out FM, so it becomes 1. So then 2 is also common. So 2 beta plus 1 FM. So using modulation index, again if we use this equation, beta equals to delta F over FM. So it can be written as generally by taking 2 common outside delta F plus FM. So this was the Carson rule. By using this, we can find the uh, bandwidth of a system. The other scenario uh, which needs more investigation is ignored. So thank you for listening, and for question answer there will be a separate session, online session, which exact date and time will be communicated later on.